at which point I pass you over to Daniel, and hopefully the wonderful tech team will sort that out for us. Great. Good, it does. You're ready.
So hopefully people can see my screen now. Let's see. Let's just get this working. Oops. All right. So yeah. So again, I'd like to thank the organisers for inviting me to all their magnificent efforts getting this off the ground and working in such a short order. I think it's been going very well. Yesterday, I really enjoyed yesterday's talks, and I hope this. I'm sure the rest of the conference will be will go well as well. This talk is going to be about some recent efforts in trying to implement space quantum communications. There are lots of people involved. I might get to at the end. Now, this is a very brief outline of the talk itself. I'll try to give a background to QKD. I'm sure that most of you, or a lot of you, I don't need to explain this, but for some people, might be good just to go over it. Why do we want to do satellite QKD? What is happening around the world? What are particular challenges? And in particular, how we're trying to address those challenges in a UK space quantum communications program called QUARC, which I lead. And if got time, maybe talk about the future directions in quantum communications in space. There's a few references down the bottom there. They're in the slides. So why do we want to actually do QKD? Now you've probably read, you've seen throughout this conference so far, quantum computing is developing at a rapid pace, and that it can threaten the security of current methods of public key security, public key cryptography, which underlies the internet today. So there's a big scramble to develop new methods of quantum of cryptography that is resistant to quantum computing attack. And one method is quantum cryptography, one of the oldest quantum technologies, in fact. And it's important that even though quantum computers may be, say, a decade away, that information which has a need to be secure beyond that horizon today needs to be sent securely, because the information is being recorded and then can be decrypted later on if that method of encryption is vulnerable to quantum computers. So quantum key distribution, a very, very quick overview of what it is. So here we've got our two protagonists, Alice and Bob. Alice represents the satellite. Bob is on the ground with a big telescope. And QKD works by sending streams of single photons, and each photon encodes a bit, a random bit. And we encode the information in polarization states typically, and these are chosen randomly, either horizontal, vertical, or diagonal, anti-diagonal. And Alice sends them one by one, and then Bob measures these photons in one of two bases, either in the horizontal vertical basis or the diagonal anti-diagonal basis, and records his results. And then they compare a subset of their results in order to determine whether there were any errors, and these errors could possibly mean there is an eavesdropper on the line. So by comparing a subset of the results, they can determine the error rate, whether there's an eavesdropper, and correct for the errors, and also, most importantly, amplify the privacy of the shared random bit string that they have shared. Alice, one that she generates, and Bob, the one that he gets by measuring the single photons. And it's provable that this method is secure up to some arbitrary security parameter. So this method is implemented. It's now a commercial technology that you can buy to install on your fiber optic network. But if you try to do this on the ground using optical fibers, then we have a few limitations. One is that it's a point-to-point technology. You have to have installed fiber, you need to run, you can't easily connect to mobile stations, end nodes, like moving objects. Very hard to run a fiber which trails from the network connection. And most importantly, it has a limited range. Because light, as it travels through an optical fiber, has experienced an exponential decrease in its intensity, then the range of QKD, because we're sending these single photons down them, is restricted to at most a couple of 100 kilometers, in practice around 100 kilometers or less. So obviously this is not good for spanning the globe. We can try to send it through the air, but again, because the Earth is curved, we can't really go very far. The longest terrestrial free space transmission was between two islands in the Canaries, and they had to go on top of two volcanoes to actually see each other and get away from most of the atmosphere. Now, this is why satellite quantum key distribution has been pursued, because we can get around this range limitation. Since in space there's no air, there's nothing to absorb the light that we're sending, we're really restricted just by the diffraction losses. A light beam spreads out and we get a 1/r² attenuation. And 1/r² is much, much better than exponential decrease. So light beams can travel hundreds of thousands of kilometers and still have a reasonable chance of being detected. The atmosphere represents a very small loss compared to the free space diffraction. Now, there are two topologies for actually implementing satellite QKD. One is the untrusted node, where we have a satellite which transmits simultaneously down to two ground receivers, receiver A and receiver B, and it could transmit, for instance, entangled photon pairs. And the quantum correlations in that entangled pair can be distilled into a perfectly secure key without having to trust the satellite itself, because you can test the correlations, for instance, using Bell inequalities, or a violation of a Bell inequality, which demonstrates that there are secret correlations in that quantum state, that shared quantum state. So this is the holy grail, where you don't need to trust the satellite to provide the quantum signals that you expect it to. Google could operate the satellite and you wouldn't worry about your privacy, because you can test that the signals that you're getting are actually secret. However, this is very difficult to do because you're trying to do simultaneous downlink and the losses are extremely high. What's more practical in the near term is actually called trusted node, where a satellite acts as a trusted courier of keys and can distribute individual keys between different parts of the world, but receiver A could be on one side of the world compared to receiver B. And then through a public broadcast of the XOR of the private keys generated, then receiver A and receiver B can then communicate securely. Now this is very scalable by adding more satellites in different orbits to cover the whole world, and can have arbitrary range, but it does have a limitation that the satellite needs to be trusted. In certain circumstances, this is not a problem, because, for instance, if you're a government who are launching and operating the satellite, then the ground receivers as well as the satellite, they all have the same security level. So you might as well trust the satellite if you're going to trust the receivers that you have also built and launched yourself. So the big seismic shift in this area came in about 2016, 2017, when China launched the Messier satellite as part of their QUEST mission. And they put all of this theory into practice. There was a lot of, the idea of SAT QKD was from this early 90s, from the 90s. and a lot of development work on the ground, but it wasn't till mid to late 2010s, or 20 teens, I guess, that it all got off the ground and implemented. And the Messier satellite was very impressive, and it demonstrated a whole suite of quantum communication tasks from space. I think the headline experiment was that it distributed pairs of entangled photons between two places which were 1,200 kilometers apart. So this is an order of magnitude greater than the previous record of 144 kilometers. It also did teleportation from Earth to space, and it implemented this trusted node quantum key distribution, linking up Europe, Austria, and in China. But this was a very, very expensive undertaking. The launch itself would have cost maybe $100 million. The development costs over several years was probably very high, because it's fairly large satellite, 635 kilograms. Now, this triggered the success of QUESS and Messiers triggered a global space race to try to implement satellite QKD. No other nation has yet replicated China's achievements, but there's a lot of work going around the world. So this is a very brief sketch of what people are doing. There are, since this article was published in 2018, there have been other efforts which aren't listed. The one I'm talking about today, which is QUARC, that is not on there. There's also been commercial efforts. So there's two commercial European Space Agency-backed consortia trying to develop commercial satellite QKD, and there's a long-term vision of linking up the whole of Europe using secure quantum communications, of which space and satellites will play a major role. There are several other CubeSat efforts, QKD CubeSat, which is a UK-Singapore consortium collaboration. There's a commercial CubeSat mission, ID6 ROCKS, and there is a mission which is going to be run by the Quantum Communications Hub in the UK. And QUARC, which I'll be talking about today, is, I guess, a precursor to that mission to develop some of the basic technologies and know-how to actually launch and conduct such a mission. So what are the main challenges in satellite QKD? Well, it's the size, weight, and power restrictions of putting anything into space. Basically, space is hard and it's very costly, and the bigger and more power-hungry and massive a payload you try to put into space, the more expensive it is. And really, we're limited primarily in this application by the size of the optics that we can put to transmit these very weak optical signals, hundreds of thousands of kilometers. And to reduce the diffraction, we really want to have the largest optical aperture to reduce the diffraction of the beam. The mass of the satellite is also limited. Satellites that we are trying to use weigh only a few kilograms. These are CubeSats. They range up to a few tens of kilograms for microsats. Geostationary satellites, they can be the size of a bus and weigh several tons, but they cost hundreds of millions, if not $1 billion to launch. Power is also very constrained. Now, getting it up there into space and getting it to work in space is a big challenge. Obviously, there's radiation. We have to have things that work in vacuum. Because we're orbiting the Earth once every about 90 minutes, then we get huge temperature swings and thermal cycling at a rapid rate. And just simply getting up there on a big rocket, the shock and vibration is something that we have to be very mindful when designing and building satellite payloads. For SAT-QKD in particular, there are a few choices we have to consider. One is the protocol that we use. We're going to be mainly talking about trusted node satellite QKD. We can talk about using discrete variable prepare and measure protocols such as BB84 or entanglement-based methods. And there's increasing interest in trying to implement continuous variable QKD in free space channels and for satellite QKD. Each of these protocols, not only do we have to worry about the quantum channel itself, but also the classical communications that is required to implement the protocols, because communications to a satellite actually is quite limited, and so we want to reduce that. The various options for encoding, polarization, time bin, time energy, OAM, orbital angular momentum, possibly is not a goer, but people have still thought about that. And obviously wavelength. In free space optical communications, wavelength and transmission through the atmosphere is extremely important. And as we try to go towards daylight transmission, then we may be going towards the mid-infrared to try to find these windows where we can get away from the solar background, but also penetration through weather. Now there's a basic design choice one has to do. One is whether we send our quantum signals up or down, and there's actually a big difference in terms of how the atmosphere affects the signal. Downlink actually is a lot better in terms of the pointing losses and the deviation of the optical signals due to turbulence. So this is one that generally we try to use rather than the uplink. Uplink has other advantages, but in terms of transmission and reduction of losses, then downlink's probably the preferable one. And the other half of the equation, Bob, the optical ground station, this is often overlooked, and it's actually it's half of the whole system. And really, we don't want to have to build observatory class telescopes and optics in order to receive these faint signals. We want to go for something a bit more portable, and hence in our project we're also looking at building portable ground stations. So the receiver not only has to receive the weak quantum optical signals, it also needs to track the satellite, it also needs to get timing information, and also do classical communications with the satellite in order to complete the QKD protocol. So what we've done is, as a preliminary study, we looked at whether a satellite constellation can actually provide, for instance, regional QKD service. So we looked at, for instance, securing UK national critical infrastructure, and this is like power stations, offshore power generation, smart grids, pumping stations, all of the critical infrastructure that could be distributed across the UK, which needs to be controlled and monitored. So, control and telemetry signals, they don't require a lot of actual data, but they do, the information, these links have to be secured. And so we modeled the UK. So on the left here, we see what the UK looks like, roughly. And we looked at both seasonal and regional variations in the key rate one would get by modeling a simple satellite constellation. So this was 15 satellites. And we see that also we have a lot of variation. And we included the weather effects. Obviously up in Scotland here, we don't have the best weather, although it's actually sunny outside the window at the moment. But typically, we don't have very great weather. But also the time of, the length of night actually plays a very big role in how much key rate we can actually generate. Because typically we can only operate during night using current systems due to background light. So these kind of studies are going to be increasingly important to see whether satellite QKD is going to be practical on a large scale, and what regions of the Earth we can actually cover effectively. So what we've done is tried to come up with a way of developing satellite QKD technology and experience in a much cheaper and faster way than, say, China has done. So one is to use Cubesats or nanosatellites. These are very small satellites. They're relatively quick and inexpensive to develop, but they allow you to rapidly prototype and test things and launch things into space. So obviously they're very small, so they're limited in their size, weight, and power, but they're still quite capable in terms of the miniaturized components that have been developed for them. So for several years, I've been working with the group of Alex Ling down in Singapore, and we have launched actually 3 missions, 2 of which have been successful, to actually develop some components such as entangled photon sources in space. So this is a picture here of a later satellite that was launched 2 years ago. And there are actually a plethora of CubeSat missions under development at the moment to try to develop this technology. So in 2015, there was a proposal, a six-nation proposal to do this. It was unsuccessful, but it did spawn a lot of missions. And one mission is QUARC, Quantum Research CubeSat, which we are running in the UK. So this is based on a 6U CubeSat. So 6U is roughly 6 liters, 10 kilograms, and it's a very densely packed satellite with a lot of systems. It's a fully working satellite system. We've developed its internal systems, you know, both the ground as well as the space side of things. This is you know, roughly what the satellite will look like inside in terms of its systems. We have to develop a way of sending these single photons over hundreds or 1,000 or 2,000 kilometers very accurately. So we have to point to about maybe 1 to 3 microradians. So we have a very yeah, well, quite a sophisticated acquisition, pointing, and tracking system to do that. And we've been developing that over the last couple of years. We have looked at space optics, the telescope design required in order to transmit these photons over these long distances, and how we're going to track the ground station from space. Obviously, these have to be very well-performing, broadband, polarization maintaining, and high transmission rate. And we've been developing engineering models. So at the moment, we're in the middle of a program to develop the engineering model of the payload, including the acquisition, pointing, and tracking system, as well as the quantum source. So the quantum source is actually based on the handheld QKD system, which is being developed by Bristol. And but we're moving to a clean sheet design, which incorporates either lasers or superluminescent LEDs, or even resonant cavity LEDs for slightly higher brightness than the micro LEDs that we were using before. The other part of the equation is the portable optical ground station, which is based on a 43 centimeter commercially available satellite, but we're developing the back-end optics, the quantum analyzer, including a active tracking. One of the main things that we have to develop is the timing and synchronization system, which can actually synchronize to within 0.1 nanosecond over the distances from space to ground. And we have to be able to identify each single pulse that is being transmitted and received, so that we can identify exactly which signals correspond to which signals. So, you know, this, I'm sort of running out of time, so I'm just going to say a last, you know, there's a lot of things that need to be done. Main thing is making sure that these systems that work in all conditions, during the daytime, and also when the weather isn't perfect as well. We need to increase the rate so that it actually is useful for more applications. Also, maybe use it for entanglement distribution in the future for the quantum internet, and also for fundamental physics experiments, which I think is going to be really exciting when we can get to these long distances and these different regimes. I'll just finish off with the team. There's a lot of people involved, including people at Bristol, but also at a company, Craft Prospect, which is actually working on a mission themselves that we're assisting them on, and a lot of the engineering development is being done by them.
Okay, thank you, Daniel. That was an excellent talk. We've overrun a bit, but of course you were presenting slides, which was my work at the end there, so I forgive you. I forgive you. But we don't really have time for any big questions. But well, David Bacco's asking, what's the average expected lifetime of a CubeSat?
Good question. We don't want them to last too long. So actually, we're trying to launch them to low Earth orbit, where they will naturally deorbit within a few years, because we don't want to clutter the near space. So we try to have it, maybe a few years at most. But yeah, but they're inexpensive enough that we can continuously replenish the constellation. So a few years at most.
Okay, good. And I think there's going to be more questions coming in now, but we're going to put that onto Slack. So if you can go on Slack and answer and have the discussions there, so that we can go on to the next talk. So we will leave you now. Thank you again. And